Hello, my name is Robert Smith and I'm with New River Community College's Academic Assistants, and today we're looking at the Q value. So what does Q tell us? Q is related to K, which is to say that they're both equilibrium constants, except K is at equilibrium and Q is out of equilibrium. And the relationship between Q and K will tell us whether a reaction is either in equilibrium or out of it. For example, if Q equals K, then we are at equilibrium. However, if Q is less than K, then we can make some assessments as to, first of all, that if Q does not equal K, then it is out of equilibrium. But we can also tell what direction the reaction has to proceed in order for it to come back into equilibrium. And when Q is less than K, then it's going to proceed from left to right. Just as a forward moving reaction would. If Q is greater than K, then the reaction proceeds from right to left, or in reverse, as we refer to in the common vernacular. So let's take a look at this problem. At the reaction's initiation, there are 0.492 moles of oxygen and 2.13 times 10 to the minus 2 moles of hydrogen, and 4.26 times 10 to the minus 4 moles of water in a 5.3 liter vessel at 537 degrees Celsius with a Kc, so that's our K value, of 2.1. Is the reaction in equilibrium? And if not, what direction will it proceed in? So the first thing we're going to do is we're going to write down what we know. We know that K is equal to 2.1. We also know that we need to look at how we can make it so that K is in formula. Whatever formula we make for Q is going to be the same that we would for K, except we're assuming that it's out of equilibrium. So in much the same way that K equals products over reactants, so too does Q equal products over reactants. But first, we have to recall that when we're talking about Kc, when we're talking about things reacting at concentration, we're talking about it in terms of molarity, or a concentration. It doesn't necessarily have to be molarity, but in this case, we're going to use molarity because we're given moles and liters. Okay? So we're going to calculate the initial molarity of each, or the molarity of each of these at the point in which we're testing. So the molarity of O2 is equal to 0.492 moles per 5.30 liters, because that's the total liters we have, and that's the total moles of oxygen that we have. So that gives us 0.0928 molar. We can do the same with H2 and with H2O. And that's what we're going to have to do. In each case, we're going to have 5.30 liters underneath. And for H2, we have 2.13 times 10 to the minus 2, so 0.0213 moles. And in the case of water, we have 4.26 times 10 to the minus 4, so 0.00426 moles. And again, we can calculate that using our calculator. We end up getting 0.00402 molar and 0.0000804 molar. You can write that in scientific notation if you like. I'm just leaving it like this right now so that I can work with it easier. If you want to do it in scientific notation, make sure that you're doing it properly, that each of them have the same exponent and so forth. So again, Q is going to be products over reactants, and our product is water. So we've got H2O, and it's raised to the second power, as you can see right here. And then we have our reactants, H2, also raised to the second power, and O2. And then we just plug in the values. So for H2O, we have 0.000804 over, and that's all squared, over 0.00402 squared times 0.0928. Again, you're leaving the units out because Q, just like K, is going to be unitless. And we end up with 12441 after you calculate it, which we're going to rewrite as 1.24 times 10 to the fourth, which gives us our sig figs. Okay? Now, we can see that this is a lot bigger than that. So Q is much, much bigger than K. Which means, just like this one, that the reaction proceeds right to left in a very expeditious manner in accordance with how fast the reaction would generally run. It's trying desperately to get from its water state to hydrogen and oxygen under these conditions. Okay? And that's it for our little talk on Q. You can read more about it in your textbook. Again, just treat it like K and then compare it with the K value to see what direction it moves in. And again, if Q does equal K, then that is your reaction is at equilibrium. So that's a very important tool, very powerful tool to tell us how a reaction will react under various conditions.